Okay. Hey guys, my name's Emma and I'm a fourth year PhD student in statistics in Adrian's cohort. And today I was supposed to cover for Adrian because he was sick, but then I woke up this morning and I tested positive for COVID. So class just had to be canceled. But because of that, I'm going to try to redo the lecture that I would have done in class today. This all came from Adrian's lecture slides that he was going to present to you. I've also seen your exam, so this should be a pretty thorough review of your exam. But as usual, make sure you study and go back and review all those chapters and don't just rely on this review to help you for your exam. So yeah, your midterm is this Friday, February 16th at 11:15. Make sure you let Adrian know if you have university approved excuse or accommodations or anything of that sort. The midterm will cover chapters 1 through 4.3 in the textbook. Also, make sure you bring your laptop or just some device to take the exam on. In my opinion, taking it on your phone would be really difficult. So I would bring a laptop and maybe a calculator, make sure you have Excel downloaded. And yeah, if you have any questions about that, just reach out to Adrian over email. Also, I believe we're going to try to put this video on YouTube, so feel free to leave a comment if you have a question about something that I'm talking about and you want me to clarify. I'll try to get back to you. Okay, so usually I would stop here and ask if there are any questions, but can't really do that, so I'll keep going. So I think last lecture you guys talked about the normal distribution, chapter 4.1, which we'll talk about really quickly today. And then you guys also did the first part of review 1. Today we are just in that open parentheses, just a typo, but today we're just going to cover the second part of midterm 2, which covers the majority of what's going to be on your exam. So where you guys left off last time is, if you remember, I think this is chapter 2, where you summarize the data. And there are different measures of central tendency, and that's the mean, the median, and the mode. And remember, there's different ways to represent the spread of a distribution as well, and that's variance. The square root of the variance is the standard deviation, and then we also have the interquartile range. And hopefully you guys remember the way you would compute the interquartile range is just that third quartile minus the first. Remember, the third quartile just means that 75% of your data is less than that cutoff point. That's your third quartile. And then the first is just 25% of your data is less than that cutoff point. And what's really important that you take away from this slide is this picture over on the right. Hint, hint, hint. You may see this again. The picture on the left shows you that, and remember, a distribution's skewness is defined by the tail. So this right here is left skewed. This middle distribution is symmetric. And this right distribution, its right tail is the longest, so we call it right skewed. And like I said, what's important is that here in this picture on the left, we have extreme points that are pulling the distribution to the left, making it left skewed. So now the mean is smaller than the median. Because we had a symmetric distribution, we added points to the left, which pulled the mean over. So it's really important when you have a left skewed distribution to know that the median is going to be greater than the mean. And so maybe the mean is not the most robust statistic to use. The median would be the best choice because it's not as affected by extreme observations. In symmetric distributions, oh my goodness, the mean is approximately, the squiggle just means approximately, equal to the median. In this case, in the picture, they are exactly on top, and you can add mode to this as well. This is a perfectly symmetric distribution. And then on the right, we have a right skewed distribution, so the mean is being pulled over to the right, which means the mean is greater than the median. And again, in this case, the best measure of central tendency here would be the median because it's robust to outliers and extreme observations, while the mean is being pulled over to the right pretty dramatically. So that's the important takeaway from this chapter. Okay. And then really quickly, we're going to go ahead and move on to probability because I think this is the thing that students struggle with the most. And if you remember, there are some rules about probability. I'm sure you know it always takes values between 0 and 1, just like a proportion would. And then the way you compute the probability of A, which is denoted P of A, is the number of ways A can occur divided by the total number of outcomes. So if we think about an example, like what does that even mean? Let's see, well, the probability of drawing a king. If you have a deck of cards with 52 cards, well, what is the number of ways that we can draw a king? Well, we can pick up like the king of hearts, the king of spades, all of that. There's 4 of them. And so there'd be 4 different ways that we can draw a king in one draw. And then the total number of outcomes, well, there's 52 cards that we could have drawn. So it'd be divided by 52. And it's as simple as that. Every probability problem can really just be broken up into number of ways it can occur divided by the total number of outcomes. But there are some rules that are going to help us along the way because, this may not always be the easiest way to compute it if we maybe have 2 events or something like that. Okay. So here we sort of get into these different rules. So remember you guys talked about what it means to be disjoint, or you can also call it mutually exclusive. It just means that these 2 events, A and B, cannot happen at the same time. And again, that means they are disjoint or mutually exclusive. So you could think of like a Venn diagram where this box represents your whole sample space. And then we have 2 events, A, and the area in the circle will be the probability of A. And then we have another event, B, and the area inside the circle B, so the green area, will be the probability of B. And we can see that the pink and the green, they do not overlap at all. And so we would call A and B disjoint or mutually exclusive events. And the way to denote this as a probability statement would be A and B. If A and B are disjoint, then that means the probability of A and B is 0. And these kind of rules are really important to memorize. They're going to make your life a lot easier when you want to quickly pull out results for the exam. So make sure, like, first step, all these different formulas and definitions. And then second step, think about what does it mean? How can I apply this to problems? Okay. And then the opposite of that would be they're non-disjoint, meaning if you drew a Venn diagram, the green and the pink bubbles would overlap. So you would say that's non-disjoint, and the probability of A and B is not 0. It's going to be some number. Okay. So we'll keep going. What I think really gets a lot of people is we then move straight into talking about independence. And I think a lot of people struggle to differentiate between disjoint and independent, but they are really 2 different concepts. So 2 processes are considered independent if knowing the outcome of one provides no useful information about another. So you can think of if we were to flip a coin twice, the first flip, say, you want to know what's the probability of getting a heads. We know that's 1 out of 2 or 0.5. And then if we were to flip a coin again, well, knowing that we got a heads the first time doesn't tell us anything about what we're going to get on that second flip. It's still going to be 0.5 for the probability of getting a heads. And so we would say those 2 coin flips are independent of each other. However, you could think of outcomes of 2 draws from a deck of cards without replacement as dependent. And I'll show you what that looks like. Okay. So what if I asked you, what's the probability of drawing a king? Just one single draw like we talked about before. I don't know why it keeps doing that. There we go. Well, like we said before, there are 4 kings in a deck of cards out of 52 cards total. But then what if I asked you guys, what's the probability of drawing a king on the second draw, given I drew a king on the first? And this is without replacement. So I picked up a king, and then I took it out of the deck. What's the probability that I pick another king? And just as a reminder, this line right here, that notation means given. So it's the probability that I drew a king on the second draw, given that I drew a king on the first. Well, we have one less king in the deck, so that's 3. And we have one less card in the deck because we didn't put it back, so that's 51. And we can see that 4 out of 52 is not the same as 3 out of 51. Knowing that we drew a king on the first affected the probability of drawing a king on the second. And so because of that, these events are considered dependent. And in fact, whenever you have draws without replacement, you'll have dependent events. So like I said before, this is an example of dependent. However, if you were to do this process and replace them each time, this would be independent events, because now the numerator and the denominator are not going to change because you put that king back in the deck. Which kind of leads me to, how can I mathematically show that 2 events are independent? And you could probably get that from this statement right here. So how do you show independence? So you could kind of rationalize it like I just did, or you can just go through these formulas, and I think that would be the easiest way to go about it in practice. So number 1, you could say A and B are independent if number 1 is the probability of event A occurring given event B already happened equals the probability of A. So again, knowing B didn't tell me anything useful about the probability of A. And you could go backwards. You could say the probability of B given A equals the probability of B. Same thing. Or the last one that you can show, and this is called the product rule, is that if the probability of A and B, this little N sign just means and. If the probability of the intersection of those events equals the probability of A times the probability of B, that means A and B must be independent. Now, keep in mind, I think a lot of people want to use this third rule as it's true all the time. It's not true all the time. This is only for independent events. So if any of these 3 statements are true, you don't have to check all, just one, then A and B are independent, and it works the other way too. If A and B are independent, then those 3 statements are true. So this is definitely something you want to memorize for your exam, and will definitely help you out and give you shortcuts and help you understand the definition. Okay. So keep in mind, as a side note, independence, I'm going to apologize for my spelling in advance. You know, I'm a stats major, not an English major. So independence and disjoint are not the same. And this is really, really, really important to understand. One does not necessarily imply the other, except for one very specific instance. And I'm going to outline this. And that is if A and B are disjoint, then they are not independent, meaning they are dependent. And you know, everyone likes to think of this in different ways. I'm going to use the formulas first, and then we'll sort of use intuition as to why this would be true. So let's think about this. If A and B are disjoint, what does that mean? I'm just going to write proof. If A and B are disjoint, that means the probability of A and B equals 0, right? We just talked about that with definition of disjoint. That's why it's so important to have these definitions memorized. And so if I want to show that they are independent, then remember I have to go back up to one of these rules. I have to show one of them is true. So let's look at 3 because that directly involves the probability of A and B. So, oh, sorry, sense disjoint. So if we look at rule number 3 for independence, the probability of A and B equals probability of A times probability of B if they're independent. But wait a second, we just said the probability of A and B is supposed to equal 0. But how can that happen? That would only happen if either the probability of A was 0 or the probability of B is 0. But that really wouldn't make sense to talk about, right? We wouldn't say we have these events that where the probability of them is 0. We wouldn't define them at all. So as long as A and B are non-empty events, meaning their probability is not equal to 0, then as long as A and B are disjoint, they have to be dependent. There is no way that the probability of A and B can equal the probability of A times the probability of B. And like I said, the key assumption here is that the probability of A is not equal to 0 and the probability of B is not equal to 0. Another way to think about this is if we draw a Venn diagram, like I said, if they're disjoint, that means their Venn diagrams would not overlap. Their circles do not overlap. So we know they do not happen at the same time. And so you can think about if we know that A occurred, that tells us information about B. That tells us there's no way B occurred as well. So they're not independent events. They are very much dependent. Knowing one tells us the other will not happen. So that's the one exception to the relationship between independence and disjoint. We know for a fact if A and B are disjoint, they are going to be dependent on each other. However, this does not work in the opposite case, which is why I said in general, one does not imply the other. And in general, they're not overlapping concepts. So does this mean if A and B are dependent, does that mean they are disjoint? And the answer is no. And a good counterexample for that would be, let's say we draw cards, 2 cards, without replacement. And remember, we already said those are dependent events. And you can just scroll up if you forgot that already. So we want to show that even though they're dependent events, they are not disjoint events. So let's just say we look at the probability of a king on the first draw and a king on the second. Remember, they're disjoint if that probability equals 0. But I mean, that we already know that can happen, right? It's very possible to draw a king on the first and then draw a king on the second. So of course, this is not equal to 0 and they are not disjoint. So one does not necessarily imply the other, if that makes sense. Okay, so I'm gonna keep going. And we already sort of talked about this a little bit in independence, but there's this concept called conditional probability, and it is a measure of the probability of an event occurring given that another event has already occurred. So again, this line just stands for given. So the probability of A given B equals the probability of A and B divided by the probability of B. And you might be asking, Emma, I mean, didn't you just tell me that the probability of A given B equals the probability of A? That was in one of your rules. right? That was rule number 1. No, that's just if A and B are independent, and I think that's something people really get confused on. So don't use that unless you know they are independent or you're trying to prove independence. So in general, this is the way we would write it. Okay. Okay, so the next topic that y'all talked about are random variables. And remember, random variables are denoted with capital letters like capital X, Y, or Z. And then we can figure out probabilities and expectations and variances of random variables. And the way you would denote the probability is the probability that capital X, your random variable, equals some lowercase little x. And that lowercase little x is your realization. So if I'm rolling a die, what's the probability that my random variable x equals a 5? Well, that would be 1 out of 6, right? There's 1, 5 on the die, and then there's 6 total options. Okay. So like I said, you can find expected values and variances of random variables, and we call this the expected value. It's just an average, and it's denoted by E of x. And the way you compute the expected value of x, or the average, and I'm just going to rewrite that, is this should be an x1. So x1 times the probability that x equals little x1 plus, and you would keep adding, so x2 times the probability that x equals x2 all the way up to xk times the probability that x equals xk. And oftentimes, we'll switch between the notation E of x and mu. They both mean expected value and average. Hopefully that makes sense. And we'll do a couple of practice problems with this too. This is a really important concept. You are definitely going to see this again, whether that be, hint, hint on the midterm or, on your final exam or something like that. Okay. You can also compute the variance. And the variance is just like a measure of spread of your distribution. And the way that you would compute the variance is your realization x1 minus the expected value squared times the probability x equals x1. And you would add all the way up to xk, your realization, minus mu, your expected value squared, times the probability that x equals xk. And you can also put this in summation notation, but a lot of people find the first easier. And the variance of x is represented either by, this should be a sigma squared, or it can be just called var of x. A lot of times we switch notation between the two. And then don't forget that the standard deviation of x, I'll write it here. Sometimes we call it sigma or SD of x. It's just the square root of the variance. Okay. Now, what's really important to note here is that the variance depends on the expected value. So if you're asked to compute the variance, you need to make sure you compute the expected value first. Again, mu is just the same thing as E of x. Okay. So the way I would recommend doing these problems is drawing out a table. Maybe I'll just go ahead and write this if you forgot. Where you have x, p of x, x times p of x, and then you would add up all of your x times p of x's, so everything in this column. And when you add all that together, that's going to be the expected value of x. And if you're confused and you don't know why, look back up at this formula. That's exactly what that is. It's just adding up all the x times p of x's. And then once you have the expected value, I'd make another column. That's x minus the expected value of x squared. Do that for all your different outcomes. And then lastly, I'd have another column that's p of x times x minus e of x squared. And if you add everything up in that column, that will get you the variance. And again, if you're confused why, compare it to this formula. It's simply just x minus the expected value of x squared times p of x for all your different combinations added together. Okay. And then if you want the standard deviation, you just take the square root of the variance that you found. Okay, so another topic y'all talked about is the expectation and variance of linear combinations. And I think maybe the phrase linear combination is not super clear. So I'm just gonna go ahead and write just sort of a simplified explanation. Linear combination just means it can be represented by a line or equation of a line. So if you remember, the equation of a line is just ax plus by equals some constant c. Okay. So if x and y are two random variables, so now we have two, then the average value or the expected value of a linear combination of them is the expected value of ax plus by equals a times the expected value of x plus b times the expected value of y. Remember here, a and b, they're just some constants. X and y are your random variables. So it works like you would think. The constants just move to the outside and you can add them together. Okay. This is really important. You're definitely going to see this again. And then the variance works pretty similarly. If x and y are independent, then the variance of a linear combination of them is just a squared variance of x plus b squared variance of y. And there are lots of proofs out there. If you're curious, why did we square the constants? I'm not going to go through it today, but you can absolutely look it up and it's not too difficult to understand. Something important to notice about this formula is sometimes in the past, I know Adrian can be kind of tricky with this. You're only going to be given problems where x and y are independent if you're asked to compute the variance. But he could ask you maybe a tricky question like, I don't know, what is the variance of ax plus by? And then maybe an answer choice would be cannot compute because we're not given that x and y are independent random variables, or don't know because x and y are independent random variables, or not given as independent random variables, if that makes sense. So just be careful about this. Most of the time you can assume they're independent, but if it's not given to you in a problem, just be careful with that, make sure you look at the answer choices, and if there's one that mentions something about independence, look at that very carefully. But in general, yeah, we can assume it's true. If it's not true, you can look it up. There's a result with covariance that we don't talk about in this class. So this is the only formula that you need to really focus on. Okay. All right. Next, you guys talked about a bunch of different distributions. You talked about the Bernoulli, geometric, binomial, and the normal distribution. And the normal distribution is going to be really, really important for the rest of the chapter. So if you're going to highlight one, it would be that. So a Bernoulli random variable models a single trial that has two different outcomes, either a success or a failure. And you can also think about it as yes or no, or 1 or 0, just binary outcomes. It takes the value 1 with probability p, and we call that the probability of success, and the value 0 with probability 1 minus p, and we call that the probability of failure. And if x follows a Bernoulli distribution, we write x is distributed as Bern P. So the squiggle, which I am sure you'll see again, just means distributed as. And an example of a Bernoulli random variable is coin flip, multiple choice question, etc. Okay. And this becomes important for talking about the geometric distribution. So the geometric distribution describes the number of trials until a success for independent and identically distributed Bernoulli random variables. We're here, remember, independence just means the outcomes of trials don't affect each other, and identical just means the probability of success is the same for each trial. Again, think of like a coin flip. Then if we can identify that this random variable is distributed as geometric, then we can say that the probability of finding the first success in the nth trial is given by the probability x equals n is equal to 1 minus p to the n minus 1. So this is just the probability of failure, and we're doing that n minus 1 times the probability of p. So that first success is on that nth time. So I'm trying to think, if we think about this as a coin flip, say what's the probability that my first head is on the 5th time? Well, that would mean we got a tail, then we got another tail, then we got another tail, then we got another tail. So 1/2 to the 4th times finally I got my last head. And you can see how that's easily a geometric distribution. Okay. And if you're wondering why did I multiply those probabilities instead of add them, if you hear the word and in my description, that should trigger multiplication. If you hear the word or, that triggers addition. That's what those words mean. So I said a head, and then another head, and then another head. And that's why it's 1/2 to the 4th times 1/2. And then for all of these distributions, you can also define their expected value and variance. Remember, you might be confused. We already talked about expected value and variance in the above slides. That was just for any probability distribution where you're given the different outcomes and probabilities, you can compute their expected value and variance. But here, somebody already did it for us. If you can identify that the distribution is some known thing like geometric, binomial, Bernoulli, normal, then we already have the definitions for you. So somebody computed this for you, super nice. The expected value of a geometric is always 1 over p. And the variance of a geometric is always 1 minus p over p squared, where again, p is just the probability of success. And hint, 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 you are absolutely going to see these things. You are probably going to have to compute a probability or a variance or expected value of a geometric. And if you're thinking what would be some clues that I would have to know the expected value of a geometric, one example would be how many coin flips would it take Emma on average to get her first head? And literally all you have to do, I think it sounds harder than it really is since we know that x is geometric in this case because it's the probability until a first success, that success being a head. Then we just plug in 1 over the probability of getting a head, which is 0.5. And that's just 2. So on average, it will take 2 coin flips to get a head, which makes sense. And that's the type of question where you would know that you have to use this expected value formula. Okay. And then you guys also talked about the binomial. This will be super important again, that you know how to identify if it's a binomial random variable, you know how to compute probabilities, and you memorized, I would memorize it because I think it's probably the easiest way to go, the mean and the variance of a binomial distribution. Okay, so what is a binomial? Suppose the probability of a single trial being a success is p, so same notation, and let x be the number of successes in n trials. So now we have a fixed number of trials. Then x is a binomial random variable, and again, you can denote it as x squiggle, which means x is distributed as bin, which means binomial, and the variables that are necessary are n and p. Then x is a binomial random variable, and the probability of observing exactly k successes in n independent trials is given by, again, the probability x equals n equals this n choose k. That's not a fraction, it's a combinatorial term. P to the k, so the probability of success times the number of successes, or sorry, to the power of the number of successes k, times 1 minus p, the probability of failure, to the power of n minus k. Remember, there's only success or failure. So n minus k, this is just the number of failures. So it makes sense, really, that we would do the probability of failure to the power of the number of failures times the probability of success to the power of the number of successes. But why do we have this n choose k term? I'll let you think about that for a second. Well, if you think about it, if I said, what's the probability that out of 4 coin flips we get 1 head? Well, then you could have head, tail, tail, tail. You could have tail, head, tail, 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 head, tail, 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 head. So if you do p to the k times 1 minus p to the n minus k, that just gets you this right here, right? That just gets you 1/2 times 1/2 to the third. But then we can also have this right here, which is also 1/2 times 1/2 to the third. We also have this one, and we also have this one. So we have to have this multiplication term that tells us how many different ways we can arrange this. How many different ways can we have 1 head out of 4 coin flips? So this combinatorial term here would just be, we have 4 flips, choose 1. And you can put this into Excel. I don't know if AJ talked about this, but equals COMBIN 4, 1. You can also compute it by using this right here, n factorial divided by k factorial times n minus k factorial. And, go back to the lecture slides where Adrian first talked about this if you forgot what a combinatorial term is. You can also plug this stuff into your calculator. And then again, you need to memorize what is a mean and a variance here. If you have a binomial distribution, well, the expected value or the average or the mean, it just equals n times p, which is super intuitive, and I'll show you why in a second. And the variance is just n times p times 1 minus p. So what kind of question would you expect to see if you needed to calculate the expected value of a binomial? Well, think about if Emma flips a coin 10 times. How many on average would be heads? I'm sure you guys could answer this right now without using a formula. But using the formula as the example, we know that this is a binomial problem. So we just have to plug in n times p. Well, n, we have 10 coin flips, and p is just 0.5. That's the probability of getting a heads. And so 5, if I flip the coin 10 times, I would expect 5 of them to be heads. Okay. And keep in mind, you want to compare the wording of these problems. So how did this example with a coin flip differ from the geometric example? Well, geometric distribution is always the number of successes, or sorry. A geometric is always, and I'm going to scroll up, the number of trials until the first success. So there's not a fixed number of trials, and you'll see words like first success usually in there. Versus down here for binomial, it's the number of successes in a fixed number of trials. Okay. So the last distribution you guys talked about is the normal. And remember, the normal is this symmetric bell-shaped curve, and it's characterized by 2 parameters, mu and sigma squared, which are the mean and the variance. And we also have something called the standard normal. That just means that the mean mu is centered at 0 and the variance is 1. And then this is the probability distribution function. You do not need to know this for this class, but all of the results where we use Excel, the reason this is so useful is because otherwise we would have to do things like integrate this nasty thing. And we don't want to do that. So we have all these software tools and Z tables and whatnot to be able to cope with the situation. Okay. So how do we compute probabilities and cutoff values? Well, this blue area right here, that represents questions where we'd want probabilities or percentiles. And then this X value, which is called the cutoff, that like would answer questions like what is the cutoff time for the slowest blank percent of athletes in a race, or what's the lowest score a student can achieve on a test to be in the blank percentile. And so pretty simple, you just type some things into Excel. So let's just say you want the probability, but you have the cutoff. Then all you have to do is p equals norm.dist. So you literally in Excel equals norm.dist, x, which is that cutoff value that you have, mu, your expected value that you're given in the problem, sigma, and then true. And then let's just say, well, what if I have the percentile or the probability, but I want to know the cutoff value x? Then x just equals, and you literally type this into Excel, norm.inv, the probability or percentile that you're given, that you have, your expected value mu, and then your standard deviation sigma. So let's take an example. Let's say average US adult height, and I'm probably gonna go over on time, but that's okay, is normally distributed with mean 64 inches and standard deviation 3 inches. And then let's say you get a question that says, what's the probability Emma is less than 60 inches? Okay, well, the probability is just norm.dist. And how did I know it was norm.dist instead of norm.inv? Well, because we have the cutoff value at 60 inches, but we want to know the probability. So this x is 60. What's the probability that we're less than 60? That's this blue region right here. So we literally just plug in norm.dist into Excel. 60 is our cutoff. The mean that we're given in the problem is 64 inches, and the standard deviation is 3. And then make sure you put true. If you forget the true, you'll get an error. Don't worry about what the true means. It's not important. Okay, so what if you're given a different question? Emma is taller than 30% of US adults, which is probably accurate. What is her height? Well, here we have the probability or percentile, it's 30%. So this area probably looks something like this. And this green area is 0.3. And you want to know, what is that cutoff value x? So again, you just plug in norm.inv, 0.3, which is your probability, your mean, 64, comma, your standard deviation, 3. And that will output the height that I would be. A good way to know if you mixed up norm.inv and norm.dist is norm.inv is going to output numbers relevant to your problem, and norm.dist is going to output probabilities. So you want norm.dist, and it is going to output a number between 0 and 1. If it ever gives you something other than 0 and 1, you've done something wrong. And obviously, norm.inv is going to give me a height in this case. So I wouldn't expect it to be between 0 and 1. They're on completely different scales. So if I wanted to figure out what my height is, given that US adult height is normally distributed with mean 64 inches and standard deviation 3, it'd be kind of weird if it outputted 0.2. I did something wrong. I probably used norm.dist instead, right? Hopefully that makes sense. Okay, so then we just have a couple practice problems. I'm not sure that I'm going to get through all of them, but I did post my solutions to them, or Adrian did. Maybe I'll go through one of these. Let's see. Yeah, let's go ahead and do this first one since we talked about the normal distribution. Okay. So exercise 4.7 states that average daily temperature in June in LA is 77 degrees Fahrenheit with a standard deviation of 5 degrees Fahrenheit. And it can be assumed that they follow a normal distribution. We use the following equation to convert degrees Fahrenheit to degrees Celsius. So it turns out that Celsius C equals Fahrenheit minus 32 all times 5 nights. So kind of ugly, but that's okay. And part A wants us to write the probability model for the distribution of temperature in degrees Celsius in June in LA. So all it wants you to do here is to say what the distribution is and then what the mean and variance is. Okay, so we just have some linear combination of a normal random variable. So I can tell you right off the bat it's going to be normal. That's just a rule. Any linear combination of normals is also normal, very convenient. So I know that C is going to be normally distributed. Remember, the squiggle is just distributed as, but we have no idea what the mean and standard deviation are going to be. So we have to figure that out. And luckily, like I said, this is just a linear combination. And so we can use our formulas. So the expected value of F minus 32 times 5 nights. And let's remind ourselves, the expected value of AX plus BY, where X and Y are random variables and A and B are constants, equals A times the expected value of X plus B times the expected value of Y. And the variance of AX plus BY is just A squared variance of X plus B squared variance of Y. Okay. Perfect. Okay. So how do I apply that? Well, the expected value, we can just, what do people call it? They call it FOIL or something. So we can just like bring over that 5 ninths. So this will just be 5 ninths times F minus 32 times 5 ninths. Okay, well, there's only one random variable here. It's not really a linear combination, but we have this constant and then we have the random variable here. So we can use this rule still. We have the expected value of 5 ninths F minus the expected value of a constant is just that constant, right? It's not a random variable. And so it's not varying. The expected value of that constant is just that constant. So minus 32 times 5 ninths. Remember, the expected value of A times X is just A times the expected value of X, so we can bring that 5 ninths out front. And we're given right from the beginning that F is normally distributed with a mean of 77 degrees Fahrenheit and a standard deviation of 5 degrees Fahrenheit. So the expected value is just 77. And if we plug all that into a calculator, let's see. You will just get 25. Always double check my math. My students from last semester can tell you that. Okay. So then next we want to compute the variance, and then from the variance we'll get the standard deviation. So the variance of F minus 32 times 5 ninths. I would start the same, just FOIL it. Well, the variance of a constant, fun fact, is just 0. Again, it doesn't vary. It's a constant, not a random variable. So just a rule that I would memorize, and it makes intuitive sense too, right? So you can just split them up and add them. So this would be, remember, we can bring the 5 ninths out front, but then we have to square it, just like this formula says. Variance of F, and then plus a 0, because the variance of a constant is just 0. So I'll just go ahead and write that. So that's just 5 ninths squared times the variance of f, which is given to you as 5 squared. Remember, it gives you the standard deviation, so then the variance will be 5 squared. Okay. And then I'm gonna cheat really quick. You'll get 2.78. Okay. Hopefully that's right. I think that's the standard deviation. Yeah, that's the standard deviation, sorry. So it'll end up being 2.78 squared. And then the standard deviation is therefore the square root of that, so f minus 32 times 5/9. Standard deviation of that is just the square root of 2.78 squared, which is going to be 2.78. Okay, so then we know to answer the question that C is distributed as a normal distribution with mean 25 and standard deviation 2.78 degrees. Okay, so then now we can start computing probabilities about C. So B says, what is the probability of observing a 28 degrees Celsius temperature or higher in June in LA? So remember, C is normal. I'm just going to write this again. With mean 25 and standard deviation 2.78. We want to know what's the probability that C is greater than 28 degrees Celsius. I like to draw pictures for these types of problems. So remember, we're centered around 25, and the cutoff point that we have is 28, and we want to know what's the probability of being greater than that. So this green region right here. Well, if we look back up at our formulas, we have the cutoff value, but we want to know the probability. So this is going to be a norm.dist problem, right? But the problem is I give you the formula for area shaded on the left of the cutoff value. So what if we have an area shaded to the right? Well, if this whole area under the curve is 1, to get the area on the right of the cutoff value, which is what we have, we just do 1 minus norm.dist. So super easy. And then again, plug in your cutoff, 28, your mean, 25, your standard deviation, 2.78, and true. Put this exactly into Excel and double check and practice with me. You should get 0.14. You'll know you did something wrong if you get a probability that is negative or greater than 1. Okay. And then we're going to skip C, and D says estimate the IQR of temperatures in June in LA. So remember, the IQR is just the third quartile minus the first. And remember, the third quartile means that 75% of the data is less than that cutoff value. So we don't have the cutoff, but we know the probability. So this is a, you guessed it, norm.inv problem. So 0.75, comma, your mean, 25, comma, your standard deviation, 2.78. And if we plug that into Excel, which again, make sure you double check me, 26.88 is what you should get. Maybe you round it a little different, give or take. And if we want to figure out what the first quartile is, same thing, but now we plug in 0.25 instead. Because remember, the first quartile is 25% of the data points are less than that value. So 0.25, 25, 2.78. And if you plug in that, you'll get 23.12. So the IQR, or the spread of this distribution, is just 26.88 minus 23.12. And that's 3.76. Okay. So that is all I'm going to do today. Just leave a comment if you have any questions, or maybe I slipped up and said something weird that you want to try to clarify. But yeah, thanks guys. Good luck on your exam.